Now we are going to think about the transition spectrum. And you can actually observe the rotational transition spectrum in the microwave absorption spectrum. And when we think about the spectrum, it's much easier to think about it as a Kaiser as a unit because the Kaiser is frequently used for the absorption spectrum, especially in the infrared region. So what we do here is the actual energy is given by here HCB, but the unit of HC is given by joule. So just include it in a B value, and then or actually ignore the HC part because it's a constant, and we can think about the energy in Kaiser, and this B also given by Kaiser as a unit, and this energy given by Kaiser is simplified like EJ equal B times JEJ plus 1. In this case, the transition energy of rotation in Kaiser also can be given by the 2B times J plus 1. So based on this, we can write how the microwave absorption spectrum look like in case of ammonium. And in the case of ammonium, the B is given as 10 Kaiser. So please stop the video and then just draw roughly how does the absorption spectrum look like. Okay. Then here's how it looks like. So this is wave number, energy, and this is absorption. So from J equal 0 to 1 or 1 to 0. So every step, the absorption peak is displaced like 2B, right? So every absorption spectrum peak, every rotation energy of state has a difference of energy 2B. This is what this equation tells you. So in this case, in the case of ammonium, it's like 20 Kaiser. Every 20 Kaiser, you should have a peak of absorption. And as a final things you have to understand is rotational transition. Transition rule, which is indicate what's kind of the necessary conditions for rotational transition, and also some of the summary here. So the energy range of rotation first is roughly about 0.1 to, there's no meanings up to 19, but it's around 20 Kaiser. So meaning this is much smaller value compared with, for example, probably you may know if you have the OH vibration, water is typically like 3000 Kaiser, which is one of the most famous vibrational energy. Vibration. This is a vibration. compared with the vibrational energy, this value is much smaller. Okay. And also, the next one you have to understand is the transition rule. Not always the rotation of state can be transitioned from one to the other. And what kind of requirement is there is molecular dipole must not be zero, right? And it means the molecule need to have a permanent dipole. Permanent dipole. So what is dipole? Is this simply if you have molecules, one of the atoms has the bias charge and positive and the negative. So that gives the dipole, molecular dipole. Because please think about this. So when the molecules are rotating around with a dipole, it's actually the dipole is changing in size, changing in the direction during the rotation, right? And what happened here is when the light is illuminating, it's kind of like plus minus is illuminated. Then that's light dipoles. The light polarization must interact with some dipole. That's why you need to have a dipole during the rotation. So if you need to have a dipole during the rotation, this molecule need to have a permanent dipole. That's a necessary requirement for the first transition rule. Okay, and here's the second transitional rule, which is the quantum number of J must be changed plus or minus 1. So you cannot change from the 0, J equals 0 to 2, or 3 to 1, or something like this. So you cannot jump. So you have to have always every one step of J must be changed. And this is obtained from the quantum mechanical calculations. And at this moment, I cannot explain without mathematical procedures for the transition rule, but yeah, please keep in mind that the quantum number can be changed step by step. So based on these transition rules, please think about which molecules can have a rotational transition by stopping the video. Okay, so with that, in this lecture, we studied the fundamentals of the rotational transition and how to calculate the rotational transition energy.